In this video, we're going to continue on with more optimization problems and do example 2 here. You have been asked to design a 1-liter can shaped like a right circular cylinder. We want to know what the dimensions, will use the least material, right? So if we own a business and we're trying to can vegetables or something like that, or whatever, then what should we make the dimensions be approximately in order to minimize the amount of material we use? Now, of course, in this problem, we are ignoring the thickness of the material, so we're just going to talk about the surface area of the right circular cylinder can relative to its volume. First off, if we're talking about volume in 1 liter, just so you know, and this is going to be something you can look up if you don't know it already, but 1 liter is 1,000 cubic centimeters. And then what kind of function are we using here? Well, we're going to minimize the surface area function, which is 2 pi r squared. Where does that come from, right? The base and the top of the cylinder. So the bottom and the top of the cylinder, the area of that is pi r squared, and we have 2 of those, of course, one from the bottom, one from the top. So that surface area is 2 pi r squared. And then the lateral surface area is 2 pi r h. All right. We do have another formula here, though, that we can work with to help reduce the number of variables. And that is that V, the volume, is equal to pi r squared times h, which we were told was 1,000 cubic centimeters. Okay, and again, we want to minimize the surface area given the above volume. All right, so here's how we do that. We need to minimize a function here, but we have 2 variables currently, r and h. Luckily, with this information, we can determine what r is in terms of h, or h is in terms of r. And in fact, let's solve for h here. H is pi r squared h is equal to 1,000. So h is 1,000 divided by pi r squared. And now we have h in terms of r, and we can use that to replace on our other function so that we only have a function of 1 variable. This is now 2 pi r squared plus 2 pi r times h, but that is 1,000 over pi r squared. This all reduces to 2 pi r squared plus 2,000 over r. And so here's our surface area function. And of course, r will need to be greater than 0. It's the only thing that makes sense for this kind of a problem here. All right, and then of course, to find our critical point, if we're trying to minimize this function with respect to r, how do we do that? Well, we find a critical point, and so 0, and how do we find a critical point? That is where our derivative is 0. So we do that 0 is equal to our derivative of the surface area function, and then let's take the derivative of the surface area function with respect to r. Well, this will be 4 pi r, and then the derivative of 2,000 times r to the negative first power is negative 2,000 times r to the negative second, or in other words, negative 2,000 over r squared. Okay, and then we solve for r. So this will be 2,000 over r squared is equal to 4 pi r, or 2,000 is equal to 4 pi r cubed. Which tells us, after solving this, let's see, we can divide by 4 on both sides. We get 500 is equal to pi r cubed. So r is equal to the cube root of 500 over pi. Okay. Then, so this would be our critical point. And one thing I'd like to point out is notice that a double prime, in other words, the second derivative, equal to 4 pi plus 4,000 over r cubed is always positive when r is positive. So the function is concave up, right? Our function is concave up because the second derivative is positive when r is positive. So over this entire interval, our function is concave up. And in particular, at r equal to the cube root of 500 over pi, our function is concave up. So we have a critical value that the function is concave up at that point. What does that mean? Well, that means that critical value is a minimum. So this r, in fact, does minimize our function. Okay? So we know this minimizes the function. Let's continue on then from there. So our surface area is minimized when r is equal to the cube root of 500 over pi, but we want to know the dimensions. That means we also want to know h. So what is h? Recall that this is 1000 over pi r squared. If we replace r with what we now know r to be, this becomes 1000 over pi times the cube root of 500 over pi, but then that whole thing squared, that term squared. What is this? After doing some algebra, I'm going to go ahead and split this 1000 up into 2 times 500, and you'll see why I do that in a moment. 2 times 500 here. This is a pi raised to the 2/3 in the denominator here, but it's the denominator of the denominator, so that's really up in the numerator. Again, you can work that out for yourself, but that you should see that that is pi to the 2/3 up in the numerator now. And of course, we have times pi times 500 to the 2/3 power. And now you can see why I factored out a 2 out of that 1000, so that left us with 500s here, so we can deal with these at the same time. So this tells us h is equal to 2 times pi to the 2/3 over pi gives us a pi to the 1/3 in the denominator. And then 500 over 5 to the 2/3 gives us a 500 to the 1/3 in the numerator. Hey, what is that? That is the cube root of 500 over pi, or in other words, that's just r. That's what our r was. So the height is actually just equal to 2 times the radius, which in this particular case, that gives us r is approximately 5.42 centimeters, and h is approximately 10.84 centimeters. Although this answer here and this answer here for h would be preferable for me. But if you wanted to know what those values were in decimals, then you can go ahead and just calculate those. All right, and that will end this particular example.